Hey everybody, so here's what we're working for. The next grade is your project, the presentation. You have to choose a curve from the list that I probably already sent you, and then do some calculus to learn some properties. Then you have to do a presentation. It's either a PowerPoint or you can print it up like on a PDF file or a Word document, something that we can all look at. So you have to make it a presentation on paper or on a video format. But you don't have to physically stand up and talk in front of people, which is great, because then you don't have to talk to me either. So, let's see. I have some news. My ferret, Coco Bananas, has survived. Come and see us, Coco Bananas. Come on. She's still alive. She's still alive, everybody. Oh my God. Thank goodness she's alive. Here, say hello to the weasel. Say hello. Oh, look at her. Such a good weasel. And then in other news, I got a haircut. Howdy, howdy, howdy. Oh, it's my annual haircut. I kind of miss my big floppy head of hair. All right, so your project is either a parametric curve or a polar curve, and we didn't get the chance to do polar before the break. So here's polar. Polar is a really easy idea, but it's tricky. It's another way to graph in 2 dimensions, completely different from x and y, the usual rectangular graphing, but we still graph on an x-axis and a y-axis. We still draw an x and y-axis, but then we have a thing. It's a number line that works like a propeller. So this number line just rotates as if it's on a pin here. It rotates around, and the function of theta, so depending what this angle is, there's this little dude who walks up and down on this number line and marks points. You don't have to ever graph by hand because your calculator, ta-da! Your calculator has a mode button, and the mode button gives you choices. Let's see if we can get this to show up. Can you kind of see it? Mode choices. So you choose polar, and when you do y equals, I'm going to do an example with you. I've chosen to do r equals the square root of theta sine theta. So you don't have to graph that by hand. But here's what it looks like. When you fire up your calculator, you tell it to graph this thing, and then in the window, I chose to do x equals 0 to pi. And, theta. Theta equals 0 to pi. Theta min 0, theta max pi. And then x goes from negative 1.5 to 1.5. Y goes from negative 0.1 to y equals 1.5. And here's what the graph looks like. It looks kind of like a potato. It's not quite a circle. It's kind of bulgy to the left. And it's not a famous curve. It's not named after anything. But we can do calculus with this thing. Now here's the 2 things that you have to be able to do. The derivative. The derivative is done through a little dodge. When you have things in polar, you can convert to rectangular by letting x equal r times cosine theta and y equals r sine theta. So these are conversion formulas. It's in case you had something in polar, but you'd rather have it in parametric, because your r is an f of theta, so the parameter is now theta. So this means that if you're ever doing a polar problem and the math is not being very nice to you, you have the option of trying it in parametric. And there's some actually famous examples where the polar curve is tough to work with and the parametric's easy to work with. Or the other way around, there's some famous parametric curves that can be converted to polar, and the polar is easier to work with. So if you're choosing from the list and the calculus didn't work out so great the first time, switch over to the other species if it's available and try it that way. So the derivative formula, nobody memorizes this. What they do is remember that you had f of theta cosine theta for x, f of theta sine theta for y, and you did product rule. Why memorize it? It's just product rule of this thing. So you do the derivative of the y, so it's f prime sine theta plus, this should have been, God, I'm such an idiot. I think I've got it upside down. The derivative of, yeah, I've got it upside down. Sorry, just caught it. It's supposed to be the derivative of y on top. So this guy should be a cosine, and that's a plus. There we go. And then this is going to be a minus, and that's going to be a cosine, and that's a sine. There we go. Sorry about that. It's in the book. But the thing that's annoying about this formula is whatever f of theta is, you're going to see these pieces that look so familiar. Here's an f prime of theta. Here's an f prime of theta. Here's a sine theta. Here's a sine theta. Here's a cosine theta. It's like, God, can I cancel anything? And you can't. You usually can't. But if you have a derivative where things cancel and it becomes simplified and it's nice, that's worth noticing because it usually doesn't happen. And then the area formula is easy. It's 1/2 of f of theta squared from alpha to beta, where these are theta measurements. So in my problem, my alpha and beta are going to be 0 to pi because at 0, it starts here at the origin, and it makes this egg shape, and that comes back to 0 when theta is equal to pi. It's because the sine of pi is 0, the radius comes back to 0. So what's actually happening is there's a little propeller here that's depositing points as it spins around. And as theta goes from 0 to pi, remember sine from 0 to pi is always positive. So I'm always plotting on the positive part of the number line. But after theta gets close to pi, the radius starts getting small again until it closes right up. It's kind of a clumsy looking picture, but it's about right if you graph it on your calculator. You have to be in radian mode, of course. Okay, so what I want to do is I want to do the area. Just look at this egg. I would like to find that area. That's my project. So here's my example project with you guys. I have a drawing, and I fired it up and did the problem in Scientific Workplace, or Maple, and I've got the answer. So now let's get that answer. And it's a nice answer. It's a doable answer. So we want to have the integral. So the area of my egg is integral 0 to pi of the square root of theta sine theta quantity squared with a 1/2 and then a d theta. So I'm just going to drag that 1/2 along and see what happens here. Now the square root squared is just theta. And I get a sine squared theta, d theta. I'll get out of the way. So you can see I just did the squaring. And now it's an integration by parts. So let me get this stuff out of the way here. Integration by parts. It's just going to take a second because it's obvious who the candidates are. I'm going to let theta be u. U is theta. That gives me du equals d theta. Very nice. dv, however, is the sine squared theta. D theta. And the v has to be, oh my God, I have to run off to the side and do the integral in my head of 1 minus cosine 2 theta over 2 d theta. And I'm not integrating from 0 to pi. I'm doing just the antiderivative. So I don't get to see if this is a 0. I can't lose this piece. It actually has a say. So I get a theta over 2. And then I have to integrate cosine 2 theta. Well, the derivative of cosine 2 theta is going to be sine 2 theta with an extra factor of 2. But I'm integrating. So I get an extra 1/4 in front of this thing. So it's a minus 1/4 sine 2 theta. If I take the derivative of this, the 2 comes down, changes that to a 1/2. The minus sign lives, and I have a cosine 2 theta, and I get negative cosine 2 theta over 2. So that's the right thing. So this thing becomes 1/2, big bracket, uv. uv is going to be theta squared over 2 minus theta over 4 sine 2 theta. All that evaluated from 0 to pi, minus the integral of v du. So I've got theta over 2 minus 1/4 sine 2 theta d theta 0 to pi. Now here's where I'm integrating from 0 to pi. I get a nice 0 there, so that saves me a lot of trouble. All I have to do is evaluate this piece. Over here, I have a sine 2 theta, 0 to pi. That guy goes to 0. Oh, I'm liking this problem. Are you liking this problem? Are you liking this problem? I'm liking this problem. So what survives over here? I've got a closed bracket on this whole thing. That's not, that 1/2 applies over here. I'll throw it on there. That 1/2 applies to everybody. All right, so I've got a theta, a pi squared over 4 minus 0. because when that's 2 pi, that's 0. This thing is all 0 anyway. So I've got theta squared over 4 minus 0, and then minus, let's see what happens over here. I've got a theta squared over 4 with a 1/2 in front from 0 to pi. And this gives me pi squared over 4 minus pi squared over 8, which is known as pi squared over 8. And that's the maple answer. We did it right. So this could be your project. That's your project. Now, what would you do? Well, you got to show the work somehow. So you could take a picture of it. You could write it out on a piece of paper, but it has to be in a way that other people can read it. If it's sloppy, I'll be taking points out. Because remember, this is a replacement test grade. Presentation is going to count. But that's as much work as is necessary. I know it looks like a lot, but you can do that. It's not a killer. And a lot of these curves, you don't even have to do integration by parts. A lot of these curves, you're going to have that nice little trick. But remember, when you're doing just the integral of this with no limits of integration, you don't get to apply that 0 trick. Okay, ladies and gentlemen, start your engines, get to work on your projects. Bye.